Hi, this is Kelsey Crane, and this is online video lecture number 1 for Earth Science for middle school teachers. The first question that we're going to work with is, where is Earth? So what's our position in space, in the universe, even in our own solar system? And we're going to cover 3 Georgia standards in this lecture. 1, we're going to relate the nature of science to the progression of the basic historical scientific models, geocentric and heliocentric, so that Earth is at the center of the solar system and the Sun is at the center of the solar system. We're also going to describe the position of Earth in our solar system, in the galaxy, and in the universe. We'll explain the motions of objects in the night sky in terms of relative position. I know that last one seems a little daunting, but what that really means is when you look up into the night sky, depending on our position around the Sun and the position of the other planets around us around the Sun, everything can kind of look a little bit different. So it's really not that bad. If you can, pause the video now and grab your Phases of Venus worksheet that I gave you in class. You'll need that during this lecture. So where are we? Well, first, we're circling the Sun. And that's obvious to us now, but we should really think about how we know that and how people have come to know that. It wasn't always obvious. So Aristotle and Ptolemy and other ancient teachers, they believed in geocentrism. They thought that the Earth was at the center of the solar system. And they thought that because their data supported that conclusion. They saw the moon go around, they saw the Sun rise in the east and set in the west. It seemed to always be going around the Earth. So they thought we were at the center. They also knew about other solar system bodies. So they knew about Mercury, Mars, Jupiter, and Saturn, and they believed that these planets also orbited around Earth, but that their orbits were a little more complicated. So this is one model, for example, of geocentrism. This is one that, for example, Ptolemy would have used. So think mid-1500s, maybe a little bit earlier. We've got Earth at the center, and then around the Earth we've got a level of clouds. And this is considered the imperfect realm. It's the realm of humans and sin, and a lot of these solar system models are deeply tied to religion. And then outside of the Earth, we've got red spheres, and these are perfect spheres. So you can think of these as concentric spheres around the Earth, where in each sphere, you've got one of the planets they knew about orbiting. So one of the planets would have been in each of these little rings, and then outside of those perfect spheres, you have the perfect realm of heaven. So again, it's very tied to religion. Now, Ptolemy noticed that some of the planets seemed to move forward and backward in the night sky. And so that was a little complication that he needed to provide an explanation for that. We'll look at an example in a minute. So what he decided was that there must be these things called epicycles. There must be little loops that planets have to make while they're orbiting around the Earth to explain that forward and backward motion. So this is an example of what that forward and backward motion looks like for Mars. It's called retrograde motion. That's what we call it now. So the red dots are Mars moving across the sky from right to left. They'll slow down, turning back to the right, and then it turns around and goes back to the left. So what Ptolemy thought was that the Mars, this little object, it must be still orbiting the Earth. It's just making a little loop-de-doop while it goes around the Earth. So here's what's actually happening. This is what really causes the retrograde motion, what we see as a planet going forward and backward. Okay, so first off, the red dot here is Mars, and the blue dot is Earth. Here's the Sun. And the Earth has a shorter loop around the Sun, a shorter orbit, and it also moves faster than Mars. So the Earth is going to make it around the Sun once per year, and it's actually going to take 2 years for Mars to make a loop. So you can think about Mars as being a runner that's running twice as slow as Earth around this track. So every one loop that Earth makes, Mars is going to make half a loop. And every 2 loops that Earth makes, every 2 orbits, Mars is going to get around just about once. So once every 2 years, there's going to be a time where Earth approaches Mars from behind and passes it. Right then. It's going to happen again, right there. So we're getting ready to approach Mars from behind, and we pass it. So what the person making this video has done is they've actually said this is going to be a starry sky back here to the left, and if I'm an observer on Earth and I'm looking up into that night sky, Mars is going to appear to land right about here. And again, that's because we're positioned behind Mars. So you can think of it as we're coming up from behind, we're ready to cross Mars's path and get ahead of it. But for now, it's going to shoot back and we're going to see it to our right. So here, Earth moved faster than Mars. So Earth came around, Earth moved from this point to this point and went farther in its orbit, but Mars only moved from this point to this point, a shorter distance in its orbit. And so when we viewed Mars from right here, it landed over here in the night sky. If we stopped the video now, we would make a line from Earth to Mars, and it might land about right here. So right now, Mars would look like it's moving from the right to the left. But you can notice that at this point, once we cross this center line, we're kind of ahead of Mars again. So as we view Mars, we're viewing it back and to the right. So it's going to appear like it's moving to the right now. And then lastly, once we get really far ahead and we start to look back, it's again going to be projected to the left. So what happens is, it looks like the planet moves from right to left, then from left to right, and then from right to left again in the night sky. So again, Ptolemy thought that we saw this pattern because Mars was actually out there making a loop, which is kind of what it looks like in this picture. It looks like a loop. So these people weren't stupid. They just didn't know any better. This is the observation that they make, that this thing was moving in a loop. And we can't blame them. Our solar system is super confusing looking. Like, if these light rings are all the orbits of the planets, here's the sun, and then these are the planets moving around the sun. Check out how complicated this thing looks once you take these rings off. This is the motion of our solar system. So in this video, it's as if the Earth is holding still and everything else is orbiting around the Earth. But if you chose the sun as the fixed position, then you'd see that all the planets are orbiting the sun. And I'll post this, so if you want to watch the rest of these videos, you're welcome to. So we have three new ideas that came into being around the 1500s to 1700s. And it's important to realize that some of these people, their lives actually overlapped. That's wrong. I need to fix that. Sorry, guys. So first, Copernicus realized that those really complicated epicycles, that they needed to draw these like loops in the perfect sphere, that all of those things could be really simplified and they could go away if you just assume that the sun is at the center of the solar system. He was able to then say that you would have retrograde motion. You'd have Mars appearing to go forwards and backwards in the night sky just because of its position between of Earth between the sun and Mars. Then you had Kepler. So Kepler was the astronomer who said that the paths of planets were ellipses and not circles. So that also complicated those orbits just a little bit, but made the model more realistic. And then Galileo was able to incorporate telescopes. And so this is a picture of actually Galileo's telescope. But Galileo caught a lot of heat from the Catholic Church, and people think that it's just because he was introducing this new idea that was contrary to the imperfect Earth with the perfect spheres around it. But really it's that he found that things in the perfect sphere, so planets and even the sun, that they weren't perfect. He was able to tell that the sun had sunspots, that planets weren't on their own, that some of them had moons and some of them didn't. And all of these seemed kind of imbalanced, and so they challenged the idea that space was perfect. So this is where you're going to need to, if you need to, pause the video, go get your geocentric and heliocentric models worksheet, and we're going to talk about how Venus looks in the night sky, what Venus would look like in the night sky if our solar system were heliocentric, and what it would look like if our solar system were geocentric. On the front side of your worksheet, it says Geocentric versus Heliocentric Model. This activity is based on the Astronomical Society of the Pacific's The Universe at Your Fingertips activity. And I've written out the directions that you would follow if you were doing this with a group of students on the front. But we're just going to take a minute and we're going to do this same activity but from a sketch. So on the back of your worksheet, and sorry for the grainy video, you've got two models of the Earth in relationship to the Sun and to Venus. So in this side, you've got a heliocentric model with a heliocentric sketch at the bottom, and over here you've got a geocentric model with a geocentric sketch at the bottom. So again, in this sketch, Venus is having to incorporate an epicycle to make the observations, or to make the pattern around the Earth instead of the Sun work. So let's start with the geocentric model. We're going to label some positions. Let's do 1, 2, 3, 4, and 5. And sorry if some of this is backwards. I'm doing it upside down. So we've got 1. Oh yeah, that 5 is backwards. Sorry guys. 1, 2, 3, 4, and 5. And then in your sketch, we're going to make 1 be the position right in front of the Sun for Venus. So there's 1. We're going to make 2 the position to the right of the Sun. We're going to make this position 3. We're going to make this one position 4. And we're going to make this one position 5. So this is what we're going to do. We're going to sketch what it would look like, what Venus would look like from the perspective of Earth in each of these positions. So in position 1, here's Earth. If we imagined looking at the sun, the cross-section of Venus that we would see would just be this dark half. So basically we would see Venus in total darkness at that point. So in spot number 1, you can sketch a circle for Venus and just color it in because Venus will be dark. Now, in position number 2, from Earth to Venus, you would see, again, mostly dark. So you could even, if you want, draw a little line perpendicular to the path from Earth to Venus at that point. And you can see that most of what we'd be seeing is darkness, and we'd see a little light crescent in one direction, in the direction toward the sun. That light crescent would be on the left side. So up here at number 2, you can draw this in and give yourself a little crescent. That would be light, and all of this over here would be dark. In position 3, we would look up. I'm going to draw that just to make my life a little bit easier. We would look up, and again, a lot of what we would see is darkness, but we would still see a little bit of light. So position 3 for Venus might be a half Venus. Position 4, we're looking at it, it's pretty much the same as position 3, but on the other side. So this light side will have swapped. All of that will be dark. And then in position 5, it's similar to position 2, but now that light crescent has also swapped. Swapped sides. So we can make some predictions here based on what we would observe if Venus were making these epicycles. So, for example, if the model of our solar system that we're accurate is the geocentric model. So, 1, we would never in this cycle see a new or full Venus. We never would see all of Venus. And also, if you can imagine, if we had put like a position 3.5 right down here, it would be the same as position 1. So in every epicycle, you would have 2 eclipses, 2 Venus eclipses, or Venusian eclipses per epicycle. We'd never see a new Venus, and we'd actually never even see most of Venus. So, kind of we wouldn't get to see a lot of Venus if the geocentric model is true. So now we can try this again with the heliocentric model, and if you want to try on your own first, I totally support that, and then come back and check your results versus what I'm going to sketch here. So position 1 is going to be the position on the opposite side of the sun. Position number 2 is going to be right about here. Position number 3 is going to be pretty close to Earth. Position number 4 is going to be over on this side. I'm so sorry, guys. Hard to write upside down. And position 5 is going to be up right around here. So again, we're going to be marking this down for positions 1, 2, 3, 4, and 5. So in position 1, the sun is in between Earth and Venus, so we're actually going to get to see all of Venus in position 1. You can just draw a whole Venus. We're seeing the whole thing lit up. Now as we move over toward position 2, we'll stop right here before we get to position 2 and draw that perpendicular line to the viewpoint of Earth. Here we're getting to see most of Venus, but with a little crescent that's colored in. And so that's what we're going to be seeing as Venus rounds this corner. And looks like the colored in is going to be on the left side. The dark side is the left side. The sun is over to this side. Position number 3, Venus is pretty much in between the Earth and the sun. So it's kind of blocking all of the sun, not blocking all the sunlight from getting to us, but the illuminated side of Venus is facing away from us. So in position 3, we'd see Venus blacked out. In position number 4, as we move going this way, you can imagine drawing that perpendicular line to Earth. We're going to see about half of Venus illuminated. And in position number 5, now Venus has moved up this way. It's going to be a similar scenario, but now with even more of Venus illuminated. Okay, so you can see that if these observations if these observations are for the heliocentric model, and these are the observations we see for a geocentric model, the way that we see Venus, the observation of Venus in the night sky, should be a really good testing ground for which of these models is more accurate. So let's go look at some real pictures of Venus in the night sky. And as we look at those pictures, we might come back to this worksheet to fill out this middle column, which is going to be what we really see on Venus. Okay, so this is what we actually see on Venus. And I've labeled these with positions that would be close to what we had labeled in class. So in position number 1, you can actually see most of Venus. In position number 2, we can see a crescent Venus. So we can actually see quite a bit of the illuminated Venus. In an imaginary position 2.5, you can actually get more of a crescent Venus. In position 3, the crescent has switched sides because Venus has moved in between us and the sun between positions 2.5 and 3. Position 4, Venus is illuminated a little bit more. And as we approach the sun again, Venus is going to appear even brighter in the night sky because it's moving back toward position number 1. So let's go fill out that worksheet. So take a second at the top of your worksheet to just write in real. We want to make sure that we're clear that we're contrasting this with real data. So in position number 1, we had a full Venus. We saw all of Venus. So that is confirming with the geocentric or the heliocentric model. Position number 2, part of Venus was illuminated. A pretty good section of Venus was illuminated. So it looked like this. Again, checks out with the heliocentric model. Position number 3, it was similar but with a little bit more of the crescent filled in, right? Maybe should have made this one a little bit thinner. Position 4 was where the crescent had switched sides because Venus moved in between Earth and the sun. And then position 5, we were getting almost a new Venus again, but there was still a little bit of darkness. We weren't quite back to position 1. So through here, Venus moved between us and the sun, which means it would have stopped at something like this at some point if we had stopped the camera at around 3.5. So we would have seen this. It's logical that that occurs between these two stages. Stage 4 is pretty similar, and stage 5 is really similar. So you can see that real observations support the heliocentric model and not the geocentric model. So there's a few other things that pushed us toward the heliocentric model, not just our observations of Venus. So again, Galileo's telescope showed us that the spheres were not perfect. So Jupiter wasn't perfect, it had moons, so clearly not everything orbits the Earth if something orbits Jupiter. And then the sun had sunspots. There were all these observations that the perfect spheres weren't actually perfect. And also, in a heliocentric model, Venus is going to be closest to Earth when it's new. So just after it's been eclipsed by the sun, and it's going to be farthest when it's full. So, sorry, this is in Spanish, but what that means is when Venus is in between us and the sun, so as the viewer, you are Earth. When Venus is closer to Earth, it's about to be new, it's just been eclipsed, it's going to be really big. And when it's farthest away and it's smaller, that's when it's going to be full. That's what we would see if Venus were orbiting the sun. And so we saw these changes in Venus, and it makes sense that if Venus is orbiting around the sun, that those changes in size should happen in a cycle as Venus moves farther away from us. So the truth is neither model is 100% true. So what actually happens is that objects orbit around the center point of mass. So if you've ever taken a plate and tried to balance it on your finger goes at the center of the plate. But you can imagine that if you put some marbles on that plate and they started rolling around, your finger would stay toward the center, but it wouldn't quite always be at the center because you'd have to account for the marbles rolling around. So what happens in our solar system is that the sun has over 98% of the mass of our solar system. So imagine all of the marbles rolling to the center of the plate except for two. You definitely want to hold toward the middle of the plate, but you'd have to hold a little bit to one side to account for the two marbles rolling around that aren't in that plate. So basically, the sun is not the center of the universe, and neither are we. It's actually a point inside the sun, not quite at the center of the sun. The finger of the universe has moved over a little to account for the two marbles rolling around that aren't in the center of the plate. So again, where are we? Well, first we know we are not at the center of our solar system or the universe. Two, we kind of have this cosmic address. So we are in the Milky Way, and the Milky Way is inside the known universe. There are actually billions of galaxies out there, and then each galaxy has millions or billions of stars. Our galaxy is the Milky Way. If you've ever been out in the desert or out where there's not a lot of light pollution, you may have seen this band. That's the Milky Way. You're staring into our galaxy. Now, galaxies, over time, they start to spin and they kind of pancake out into a disk. And so when we're looking out, what we're doing is we're looking along that disk. So this is the Milky Way galaxy. There are other galaxies out there, which, I mean, you probably know that there are galaxies, but all these little bright spots that look like clusters of stars, those are galaxies. So if we have this pretend cylinder, the cylinder is the observable universe. Basically that means that light from out here hasn't traveled to us yet. So there could be stars all over out here. We just haven't seen them because their light has not had a long enough time to travel all the way to Earth. So within this observable universe, there's this little supercluster called the Virgo supercluster, and we live inside of that. So the galaxy is actually, sorry about that guys, the galaxy is divided into superclusters, which are groups of galaxies. So each of these dense clouds in here, those are all superclusters. So again, here's our supercluster. It's pretty small, going down in the middle of this cylinder. And then the Milky Way is the galaxy which is in this thing called the local group in the Virgo supercluster. So we've got our local galactic group. These are the galaxies in our local group, so we've kind of zoomed in a little bit more. And then if you zoom in a little bit more on this local galactic group, you would get these galaxies. So people actually can usually name the Andromeda Galaxy. It's kind of like a star kindergarten. There's lots of young stars going on in here. And then we've got us in the Milky Way. So there's our galaxy. And you can see that this kind of has that pancake shape that I talked about earlier. So just to recap, there's the observable universe. Inside the observable universe, we have the Virgo supercluster, because to kind of, you can think of it like the country and then it's divided into states. So the universe is the United States, and then each of these superclusters is a state. So maybe we live in Georgia in the Virgo supercluster. And then within the Virgo supercluster, there's all of these other galaxy groups. And so we're in the local group, so maybe we're in Athens-Clarke County, and then within Athens-Clarke County, we're divided into neighborhoods. And so we've got our Milky Way galaxy and the Andromeda Galaxy and some other smaller galaxies. So we're actually not even in the center of our own galaxy. We're actually in one of the arms. So these arms are organized as the galaxy matures and spins, and we're in one of the outer arms. So the center of the Milky Way is a supermassive black hole. It's about 3 to 4 million times more massive than the Sun, and it's made out of a galactic bulge and spiral arms. So this is the bulge, that's the galactic bulge. These are the spiraling arms, and those are going to be the key parts of any mature galaxy. And before there were these arms, there were just like clumps that were rotating around the galactic bulge. And as it spun and as it matured, those clumps kind of spread out into arms. So not all galaxies look like this, especially not when they get started. So just a fun idea that you might want to do with your students in the future, you could have them fill out a postcard from Earth, or a postcard to Earth from them visiting in some other galaxy. And if they did that, they would have to figure out where we live. And so they might do something like Earth and third planet in our solar system, in the Milky Way galaxy, in the local group, in the Virgo supercluster, in the known universe. And we live in this cool galaxy. There's other galaxies nearby. Maybe they're sending a postcard from Andromeda, and they say something like, there's 1 trillion stars here, and we have all these other stars in our galaxy. They could make these really cool postcards from one galaxy to another. So just keep that in mind, and also not trying to depress you, but Andromeda and the Milky Way are actually moving toward each other. So in about 4.5 billion years, we're going to collide. And so the planets and the stars from Andromeda will crash into our planets and stars, and everything will go haywire. So that's all I have for you in this video. Thanks for doing your homework. Bye.